All hail the Imperial Guard. Good morning. So we're going to finish up here on Chapter 12, the chapter on kinetics. We've talked about molecularity. We've talked about first order reactions and all that. Now we're going to collision theory. And really about the whole thing. If you're ever going to get chemicals to react in a chemical reaction, molecules have to collide. And the thing is, concentration will affect the rates. The higher the concentration, the more you're going to likely have collisions because there's more of it, more chances. But it's not enough to have a lot of molecules. They've got to crash into each other hard enough. Naturally, the temperature and the rate would also be connected. If you're looking at a higher temperature, you're going to get more collisions. Why? Energy. And really, only a small number of collisions will produce those reactions. So here we have an example. We have in this graph here, we have potential energy, we have reactants here, and we have products, and the reaction coordinate. You could look upon that as time goes on. Okay, that would be pretty much the idea. So with that, we look at something called the activation energy. Now, the activation energy is the energy needed to get that reaction going to completion. Now, there is something called the activated complex because when the reactants start to break apart and start coming together, there's a transition form in there, and that's what we call the activated complex. Now, ultimately, the delta E, the change in potential energy of our reaction, is based off of where did the reactants start, what energy level, and what is the energy level of the products. Now, in this case here, since you see the energy going down, it would be reasonable to assume that that's an exothermic reaction. Now let's get back to that transition state here. If we were to go and take 2BrNO, okay, and we were able to go and get the reaction going, so there's where you go. You've got yourself a BrNO, BrNO, and notice how the BRs are connected. That's part of the transition state. In other words, it's in process of changing. Okay, and at the end of it, when we're done with the reaction, you got 2NO plus Br2. All right, let's look at some terms here. Activation energy, minimum energy needed to make the reaction happen. Now, transition states, also known as the activated complex, this is the arrangement of atoms at the top of the energy barrier. That's a pretty important idea. Arrhenius said that the reaction rate should increase with temperature. It makes sense because at a higher temperature, more molecules have the energy required to get over that barrier. And the number of collisions with the necessary energy is going to increase exponentially. Mathematically, it sounds perfectly normal. So this is the Arrhenius equation. It's going into one of the most important relationships in chemistry. I'm not going to worry too much about the Arrhenius equation here. It's not a big deal, so I'm not going to panic. Now, let's talk about activation energy and rates, the final saga. Okay, there is an activation energy for each elementary step, and that activation energy determines our K, our constant, for the reaction. Okay, and that's the formula that you're seeing there. The concentration of A to the E, the natural log, negative energy, the activation energy divided by R times T, the temperature. So K is going to determine the rate. And again, like how we did the passing of the golf balls in class, the slowest step, the rate determining, has to have the highest activation energy, which makes sense because you need the energy to get over it, even though it was the slow step. You still need to make it go. So here we go. Here's a reaction that takes place in 3 steps. Step 1, the first step is fast, so you don't need much of an activation energy going on there. Now, you're wondering, hey, what's going on here? Well, if we were to go and look at the vertical column here, that would be your potential energy. If you're looking at the horizontal, the y-axis, you're looking at your reaction coordinate. You could look at it also as the reaction progress. Now, you've got a reaction here that takes 3 steps. First step is a fast one. You don't need much activation energy. Now, the second step is our slow one. That's determining the rate of our reaction. Okay, and that you need a high activation energy for it. And then, of course, the third step is pretty fast. You don't need much of an activation energy for that. So the second step is rate determining. Now, in there, you also have intermediates. Because it's a three-step reaction, you're going to have intermediates that are going to be formed. It's a process. Think about it that way. A chemical reaction is a process. Okay? Now, in that, when you have those intermediates that are made, you also have those transition states located at the peaks here, here, and here. I don't know if you're getting to see that on the screen recorder, okay? But the activated complexes or transition states, those match with achieving the activation energy, okay? And then you have the intermediates that are formed. Well, let's get into catalysts. You guys have we've talked about catalysts before. So you speed up a reaction without it being used up in the reaction. Now, over time, a catalyst does get worn out. But in terms of making a reaction speed up by lowering the amount of needed activation energy, it turns out that the catalyst doesn't get destroyed, it doesn't get used up. It does wear out over time, though, like everything else. Now, enzymes are biological catalysts. Homogeneous catalysts are in the same phase as the reactants. So let's say all our reactants are in solution. It is aqueous. Our homogeneous catalyst would also be aqueous. It would also be in some kind of solution format. If our reactants are gases, and our homogeneous catalyst would also be a gas. So that's what they're saying when the catalyst is in the same phase as any of the reactants or all of the reactants. Now, a heterogeneous catalyst is in a different phase as the reactants. So we can look at it where if you have two aqueous reactants, okay, and your catalyst is a solid, that's a heterogeneous catalyst because it's not a liquid, okay? If you have two reactants that are gas and you put in a liquid catalyst or an aqueous catalyst, that's a heterogeneous catalyst. So how do they work? Well, they allow the reaction to proceed by a different mechanism, and that would be a new pathway. Now, that new pathway has a lower activation energy. More molecules will have this activation energy. You don't change the delta E. Not really. So here's an example where we have hydrogen bonding to the surface of platinum. That's what PT means. Okay, now when the hydrogen gas bonds to the surface of the platinum, it actually breaks apart the hydrogen bonds. Okay, heterogeneous catalysts. So here you go, you got acetylene there, C2H4, and there's a platinum surface. The double bond will break and bond to the catalyst. Okay, so the double bond breaks and now bonds to the catalyst. That's your acetylene. The hydrogen atoms will now bind with the carbon. So they leave the platinum and they connect with the carbon. And now you have C2H6. Okay. So homogeneous catalysts, on the other hand, okay, let's bring this back. The last few slides here, we're talking about what happens with a heterogeneous catalyst. The C2H4 is a gas, acetylene gas. The PT surface is platinum, it's a solid. And that just shows you how it connects and how it affects and how it breaks up. This is what makes the reaction going from acetylene to C2H6. It's early in the morning and I can't remember exactly what the C2H6 name is. I'm sure you guys do. Okay? Now, if we look at homogeneous catalysts, now remember, they're in the same state as our reactants. So chlorofluorocarbons catalyze the decomposition of ozone. Well, that was an issue. Remember, ozone is a layer above the Earth. It blocks out 95% of the UV radiation from the sun. Chlorofluorocarbons, also known as CFCs, they typically served as a propellant in the old school spray cans. But propellant is something that pushes your spray out of the spray cans. The problem is that it does damage to the ozone. But it is a homogeneous catalyst because the CFC, the chlorofluorocarbon, is the same state as the ozone. Ozone is a gas. Chlorofluorocarbons are also a gas. That's a homogeneous catalyst. Now, enzymes regulating body processes, you have protein catalysts. They are also homogeneous catalysts because they affect stuff that's going on in our cells, for example. So that would be another homogeneous. Solid reactant, solid catalyst, boom, done. Let's move on here. So let's look at catalyst rates. Now, catalysts and rates, they do speed up the reaction, but there is a limit to what they can do. If you go past a certain point, adding more reactants will not affect the rate. It's not going to change it. And if you look at zero order, well, if it's zero order, it doesn't matter what your concentration is. It's not changing anything. Okay, as we wrap up. So here's a catalyst and rate here. So concentration of reactants on our horizontal, we have our rate in the vertical, the rate of the reaction going. There is a certain point that what catalysts will do, they'll help speed up the rate of the reaction. That's what you're seeing here. And if you look at the concentration of reactants, okay, there's a certain point that this line is flat. What do we mean it's flat? It's flat in that you cannot increase the rate even though you've added the catalyst. This is just illustrating what was in our previous slide. Catalysts speed up a reaction, but only to a certain point. Past a certain point, adding more reactants doesn't change the rate. And when you look at something like a zero order reaction, it doesn't matter. We don't have that many zero order reactions. Okay, guys, that is the end for Chapter 12, Kinematics. I hope this is benefiting to you, and I will get this out. All hail the Imperial Guard.